And that's where the trio is. And then if you just walk to this room over here, you see that's the GE MR750W. That's the console room. And then you can go into the magnet, and that's the scanner. So yeah, so hopefully that gave you a good tour of the Li Ka-shing and the Brain Imaging Center facility. You have some idea of what's going on. So you can do lots of experiments here. You see there's actually a subject inside right now being scanned. So some people are really into their scanners, such that they even went and dug this whole basement. And we were able to recreate the scanner room. All right. Any questions?
Yeah, who made this?
It was a collaboration between this particular, I mean, Blockley, it's students did. It's a whole student endeavor that was last year, where a student decided to implement the entire Berkeley campus, you know, on Minecraft, and they had even a commencement, which I thought was pretty cool.
It's
On
very
Minecraft.
realistic.
And this particular implementation of the Li Ka-shing Imaging Center, that was your truly and my daughter's. So that we recreated it. So. All right. Where are we? Can everybody see the screen? Everybody had a good wet weekend. All right. Well, thank you everyone for they're putting their cameras. Really appreciate it. It's always nice, you know, to kind of feel like as if I'm teaching somebody, which is nice. Today we're going to continue on. So we finished chapter 4, and now we're continuing on to chapter 5. Okay, so chapter 5. Before that, a little bit art. This is a haiku written by Dwight Nishimura back in 2012. I'll read it for you. Recon runs all night. K-space, image space, now done. Uh-oh, artifacts. There you go. If you end up writing some haiku about MR, please send one to Dwight Nishimura. You will really appreciate that. He used to give you know, challenges for people to write MR haikus. So he's really into that. All right. You're unimpressed, but I don't care. I'm still pretty impressed. All right. So last time we talked about the block equation, right? We derived each component of the dynamics of the spins with respect to both the applied magnetic field as well as relaxation, and we're able to come up with some description. So the first one was minus gamma B cross M, which is really the interaction of the magnetic field with the magnetization. And that cross product results in a precession. So the solution for this would be a precession. So no loss of length. A length is being preserved of the magnetization vector, but then it rotates, and it rotates about the B field, the applied B fields, whether it's B0, whether it's B1, whether it's B2, or the gradients. Then we came up with the transverse decay. So that's a component which it's described pretty much by a parameter T2. Okay, so that's the loss mechanism of how the transverse component, Mx and My, decay over time. And the solution for this is the exponential decay. And then the last bit was the recovery of the longitudinal component. So the longitudinal component will then relax and recover back, if you look at the solution, to magnetization M0. Okay. As I mentioned, this equation, this is the block equation, it's phenomenological. So it fits observations pretty much and was derived by Felix Bloch. And it describes most of magnetic resonance imaging. There are certain situations where things actually don't really obey this type of exactly this dynamic. And in those cases, we will either see an artifact, or we'll, I'll just tell you, oh, we see this artifact because really the derivation, the block equation doesn't really represent it that well. There's another mechanism that is happening. And so you're seeing, for example, there are some sequences where fat becomes brighter than it's supposed to be. And that is due to other effects that cannot be described using this, using this equation. So you have to generalize it to some other, for example, in particular, when you have some coupling between spins, that cannot be described using this equation, these equations. Okay, so now we're going to have a plan, all right? And our plan is the following. We already derived the math for each one of those elements, and we put them together. So we derived the precession, we derived the relaxation. We put them together in the block equation. And now we're going to solve the block equation. This is a linear dynamic equation, linear dynamic system, and we're going to solve the block equation for a couple of special cases. So one case would be excitation, which we'll talk about in chapter 6. So this we'll talk later. And then we're going to talk about reception, which is right now. In the reception part, you're going to see that we're going to effectively derive K-space again. Somehow K-space will fall off the fact that we are applying gradient fields in the reception part, and you'll see how it just shows up from the solution of the block equation. And that would lead us to, once we understand that we're actually sampling in the frequency domain of the object, then you can derive certain pulse sequences that would lead you to sampling an image in a way that you'll be able to reconstruct it appropriately. Okay, so that's kind of the plan. And so hopefully we'll go over this today. My hope is to cover as much as the pulse sequence and trajectories as possible, such that you'll be able to solve homework in a without any significant issues. Any questions or comments about last time, administrative, anything that before we move on? Nothing? So if you scan with a Minecraft scanner, what kind of images do you think you actually get? Probably with blocky artifacts. Ha ha ha. Yeah. No? I see people smiling, I just don't hear anything. Can you hear me? Can somebody say something? Can somebody say something?
Yes, we can hear you.
Oh, thank you. All right. Okay. So this is the block equation in the rotating frame, if you remember, where the rotating frame. So this is the B field in the rotating frame, and the B field is pretty much the gradient field. So G dot R. R is a position vector that points in the K direction. So this is spatially varying, right? This component is spatially varying. And then we've got the B1 field either applied in the I direction or in the J direction. Okay. All right. So in matrix form, you can write the entire linear dynamic system in this particular way. Okay, so m dot x, m dot y, and m dot z equal to, basically this is the cross product that we described before, right? Like whenever we write minus gamma b cross m, this is effectively this matrix. And whenever you have a cross product, you have zeros on the diagonal. Okay, so you'll have the zeros on the diagonal, so all the eigenvalues would be 0. When the eigenvalues are 0, then pretty much there's no, it's only just rotations. So it's either rotations or reflections, and there is no loss of this vector, pretty much. So this part here leads to precession, and so the components that you can kind of see is gamma g dot r, or in these position will be the B1 field. So this is the contribution of the RF field, whereas these two, so again, this is the gradient field, how it interacts, and that always leads to rotations in around the z direction, and these components belong to the B1 field. Okay, so these would lead to precession. Then you can have another term, which is pretty much relaxation. So minus 1 over T2, minus 1 over T2, these affect the transverse axis, while minus 1 over T1 affects the longitudinal direction. And then you have another component, another here, which is 1 over T1 times M0. And so you can just write the entire linear dynamic system in this particular way. And when you add all these matrices together, this is what you get. So you can call this matrix A. You can call this vector M. This is vector M dot. And you got yourself M dot equals A times M plus, and that is often what it's called the U, like the input vector, times M0. And so if you learned anything about linear dynamic systems, you can see, oh, this is the evolution matrix of the state space. So if you think about a state space equation, this is the state, the magnetization is the state, this is how it evolves over time, and then this is considered the input. Okay, and just a linear, in a typical linear dynamic system, this is how it's described, you know, state evolution and then input. And so you can kind of think of the T1 as being the source of the signal. That's where energy enters back into the system such that you can excite it again. Without this part, the magnetization will always go to 0, right? Whenever you have relaxation, this part will always lead the magnetization to 0. The only way for it to come back from 0 is to have this component here, which results in the MZ component growing. Okay, so T1 is really considered the source of all signal. Now, one thing that if you actually think about this, yes, this is the magnetization vector, and it is unknown, but it also has a spatial distribution. So it's not just mx, my, and mz. It's really mx, my, and mz as a function of r. It's just as a function of space. So x, y, and z. Okay, so there's effectively many of these that we need to solve, right? We can solve for every voxel separately, but really they have a distribution throughout space. And really, what we want to do is we want to manipulate this vector somehow by changing B1, by changing the gradient, such that we're able to decode or infer what is the spatial distribution of mx, my, and mz throughout the space. And that is pretty much is imaging. What's imaging is about. It's figuring out what is the spatial distribution of mx, my, and mz. And we can probe basically this magnetization. Remember that what we get is we can only observe mxy, right, directly, and we cannot observe a single mxy. We observe the contribution of all the spins within the volume, right, throughout the volume. So the only thing we could do is by changing B1 and by changing G, and by recording what is the contribution of all this magnetization, we can try to infer what is really distribution of magnetization throughout the volume, which is imaging. And this is what we get today. Now, there are two special cases here. The special cases for reception is that we don't apply RF while we receive. First of all, it will be very difficult to receive anything if you're transmitting a strong signal at exactly the same frequency. So think about me trying to listen to you while I'm shouting. There's just no way for me to be able to hear what you're saying because I'm shouting and all I hear is myself. Okay, so if the RF transmitter is going to transmit and we're going to turn on the receiver at the same time, pretty much we're going to blow the receiver away. I mean, the receiver is just going to blow because the amount of power that the receiver is going to be seeing is going to be significant, and it's going to actually can actually damage the receiver. So while we're acquiring the data, we're not transmitting anything. We're just listening. So B1X and B1Y are 0. Okay. So in that case, in the reception, we're going to acquire the data. We're going to apply GX, GY, and GZ in a certain way that will give us some spatial encoding. And you're going to see that there's going to be an explicit solution for this case. And we're going to cover that, that today. The excitation is also very interesting. In the excitation part, well, there we're not going to receive any signal during excitation. Then it's okay to apply a transmit field, the B1X and B1Y, at the same time, perhaps as gradients. Okay, so both the gradients and the RF are going to be applied at the same time. Turns out that this is actually a nonlinear problem. It's actually quite complex. There's really no general solution for a set of equations. There are actually many solutions for special cases. And so we're just going to cover some of these solutions for special cases. We're going to talk about hard pulse excitation, some selective excitation, and so on and so forth. But in general, this is not a trivial problem, solving for the dynamics in the case of RF and gradients when they're on. Okay, at least for the design point of view. Of course, if I tell you I'm going to apply B1 and G and so on and so forth, yes, it's very easy to then derive what is the resulting magnetization. But if I want to figure out what the magnetization is by applying certain B1 as well as gradient fields, well, that is a very hard problem with many solutions. So we're going to cover only part of those. Okay. So during reception, the magnetization is really a function of the vector R. Vector R, if you remember, is X, Y, and Z. Okay, it's a vector of position, X, Y, and Z. Right? But is also a function of T, right? It's a function of time because the magnetization is evolving. It's always evolving somehow. It's either precessing or decaying, right? So it has to be a function of position, and it also has to be a function of time. Okay. Now, in order to derive things, we're going to assume a few things just to make it easier. We're going to assume a single constant T1 and T2. So we're going to assume that the tissue or the, I guess the spins that we're going to look at have a constant T1. So it's just a one value, constant T2. So again, one value. Well, you have to understand that in reality, T1 and T2 depend, of course, on the type of tissue. And so they also are a spatial distribution. So T1 and T2 have a spatial distribution by themselves. We're going to ignore it right now. In that case, our magnetization vector, M vector, which is a function of position and is a function of time, is going to look like MXRT, MYRT, and MZRT, all this transpose. Okay. So how many unknowns do we actually have? How many unknowns? Can you enumerate them? What's going on? Well, what's all the silence? Get your tongue?
It depends on
M?
spatial resolution.
Ooh, okay. So first of all, they cannot be enumerated, right? The spins, you know, we can think of it as almost infinite number of spins that are distributed in space. Throughout space, space is continuum. The concentrations of spins within a volume is, you know, arbitrary, right? So there's almost infinite number of spins if you think about that. And the space is on the continuum, right? So obviously, this cannot be enumerated, right? The other thing is time is also continuous. So while we are interested in looking at the magnetization as a function of space, if you also wanted to look at it as a function of time, I mean, there's also an infinite space over there, right, of the continuum, which is time. So what will happen is that when we actually go and try to solve for an image, we're gonna have to discretize that problem somehow. So we're gonna decide, oh, we're gonna solve this with a certain resolution over a certain field of view, and then we're gonna have a finite number of variables to really solve for. But you have to understand that this discretization is going to have consequences which are often result in artifacts, and those artifacts you'll see are, you know, some ringing, blurring, and things like that. Okay, so you have to understand that. Now, we would like to make an image of this magnetization as a function of space by using time-varying gradients. We have the vector G. I mean, remember, we don't apply any RF. Now, all we're doing is just using gradients to make an image. So we have these three gradient fields, Gx, Gy, and Gz, as a function of time that we can apply such that we'll be able to maybe create an image of, or be able to resolve what is this magnetization, okay, distribution. This is not a trivial problem. And to be honest, the fact that people have realized that this can be solved using, for example, a Fourier transform, this is a huge achievement because it allows you very easily to actually to solve something that looks like a very complicated problem. Okay, so if I remove the B1 field, remember the B1 field were affected over here, then this is my linear dynamic system. Okay, again, this is precession, right? Well, the off-diagonal component are resulting in precession. The diagonal component result in loss, so relaxation, so decay, and this is the recovery of the magnetization in the in MZ. Okay. Now, if you stare at this long enough, there's something that actually appears here. If you stare at this long enough, you can kind of realize, hold on, mx dot and my dot depend only on mx and my. Right? mx dot and my dot depend on mx and my. They don't depend on mz. At the same time, mz dot only depends on mz and 1 over T1 times m. It is not dependent on mx and my. Can you see that? Which is very interesting. So effectively, we have here the fact that we don't have an RF field that decouples the dynamic of these linear dynamic system into two independent equations. one solving for mx and my, and the other one solving for mz, because mz only depends, mz dot only depends on mz, and mxy and mxy dot depend only on mx and my, then we can solve for each one of them separately. Okay? So for the reception case, this is actually quite nice. Now I have a linear dynamic system for mx, mx dot and mxy. So this is a very simple linear dynamic system. Okay. You can very easily see that there's going to be some rotation, right? This is the cross product, cross element that will result in some rotation, and the diagonal element will result in the transverse decay. And then the MZ component, well, I mean, what I have here is a decay and recovery, right? So that's effectively what's going to happen. We're going to see some recoveries to some equilibrium state. So the solution for 2, you know, just for the MZ part is very simple, right? So MZ, R, and T, the solution is effectively, I mean, we just need to integrate it, will be M0R plus MZ R at times 0 minus M0R E minus T over T1. So effectively, I mean, we already kind of solved this before when we solved for the longitudinal component. What we see is that the initial magnetization that you have, so whatever magnetization you had is going to decay with E minus T over T1. And then you're going to see another recovery towards equilibrium magnetization. So at infinity, at T equals infinity, this magnetization will result in M0. And at T equals 0, you're going to basically see MZ at 0. Okay, so this is we already seen last time. Very simple dynamic. Effectively, what's going on here? If we have some magnetization, the Z component. Uh-oh. Uh-oh. There's somebody visiting. Somebody's visiting Berkeley and sitting in my desk. You want to see? Never mind. Let me quit. Somebody actually went into Berkeley and now it was in our scanner room. I thought that was cool. All right. Never mind. So our MZ component effectively, like we saw last time, if let's say we start at this position, then it will be kind of an exponential recovery to some equilibrium magnetization M0. Okay. And this here, this point over here would be M at T equals 0. Okay. So it will be exponential recovery of the magnetization. Any questions up to here? So what role MZ has to do really with the imaging part? First of all, can we measure MZ? Do we measure MZ when there's precession? No. So we can't really measure this component, right? So this component doesn't produce any signal. Yeah, it grows. It grows while we're making an image, but it has nothing to do with the signal that comes out. Of course, if we wait and we excite again, yes, they will have to do something. But during the imaging part, basically this dynamic doesn't contribute anything. Okay, so it doesn't produce any signal whatsoever. Just the MZ component grows, but we don't see anything in the signal itself because it's not in the transverse plane. Only the transverse component is the part that is actually making a signal that we can pick up. So now let's look at what's happening in the transverse plane. Okay. All right, let's look at MXY. So MXY, this is the dynamics that we have, right? MX dot, MY dot equals -1 over T2 you know, all that stuff, right? So these are the decay components, these are the precession components, and they multiply mxy. Now, in the past, it was easy to work, instead of working with mx and my separately, it was very convenient to create a complex number out of mx and my, such that it's the mxy component, which is a complex valued signal. And we're going to use this trick again. We're going to take equation A, which is this equation, and we're going to take equation B, which is this equation, and we're just going to add A plus I B. And we're going to solve this in the complex plane, okay, with complex variables. It's much more convenient. And the way to do it is pretty much saying, you know what, mx dot plus I my dot equals to what? Well, minus 1 over T2 multiplies mx. So that multiplies mx plus gamma g of T dot r multiplied by my, right? This component multiplies by my. And then plus I times the other equation, right? Okay, well, what do I have? I times what? I times what? Gamma g dot r, so minus I gamma g dot r. All of this is multiplied by mx, so it's multiplied by x. And then minus 1 over T2. Of course, don't forget the I, right? Multiply by I. And that multiplies by my. Okay. So all I did is I took this equation and this plus this equation multiplied by I. And so from linear algebra, this is what I get. Okay. Well then, you know what you could do? You can start massaging it. And I want to massage it such that it all is going to look like variables of mx plus I my. I want to see mx plus I my everywhere. I want to see mx dot plus I my dot, and I want to see all this, you know, the same form. So I can replace this variable with a variable which I call mxy, which is a complex variable. Okay, so what do I do? Well, if you can see, you know, I can try to join a few things together. So again, just by doing some massaging of all these things together. So here's, I have, let's see, here's a T2 over here. This is a T2. So minus 1 over T2, mx plus my will give me this component, right? So I can erase this part and I can erase this part. Okay, this gives me this. Okay. All right. So now I'm left with this part and this part, right? And so you can kind of stare at this again and see kind of what we have. So what did I do here? Here I have minus I gamma g dot r times mx, and this is this, right? This is the same argument as this one. So let me cover this one, and that ended up being over here. And so what I'm left is this component over here, but I want it to look like mx plus I my, right? So there's no I here, right? And so what I'm going to do is I'm going to put a minus in front of this, and I'm going to put two i's. Now I times I is negative. Multiplied by this negative is plus, right? So then it results in this exact same thing. And the reason I did it is because I wanted to look like something like I my, right? So then from here, it's pretty trivial to actually go to the next stage and saying, you know what? Here's really the dynamic equation. It's mxy dot equals to, and then all I did is really coalesced all the arguments, right? I took all the arguments here. I called this mxy. I call the I over here and the mx plus IMY, I took it from here and I coalesce them, and this is really the dynamic that I get. Okay. If you don't believe me, just go over it again and see how very easily you can go from the previous derivation into this equation. And so now I have mxy dot equals to -1 over T2 minus I gamma G T dot R, all of this multiplied by mxy. Now that is a very simple dynamic equation with a single variable, right? So that's a nice thing because now it's just a single variable that we have to deal with, although albeit complex value, but who cares? Still a single variable. So it's very easy. And so then if I move if I move this to the other side, then I've got this homogeneous differential equation, mxy dot plus this, equals 0. Okay, and this I can solve. How can I solve this? This is just an ODE. Well, one of the tricks is solving using an integrating factor. I don't know if you remember ODEs. Who remembers here ODEs, how to solve this? I'll just briefly mention this again. If you don't follow too much, it's simple ODE. You can go back and see how the derivation, but the integrating factor, it's a simple has a simple solution. So given an ODE that looks like this, y prime plus p of x multiplied by y equals some q of x. This is the form. Is that form fits with what we have? Let's see. We have something prime, some function multiplied by itself, right? So it is the same form that we have, right? So you can think of this as y prime. This is p of x, right? This is p of x multiplied by y, right? And then equals 0. So our q of x in this particular case is 0. So what we do is we multiply with some integrating factor m of x. Okay, some arbitrary function m of x, such that if you pick the right m of x, then if you multiply m of x here, m of x here, and m of x here, then you can write the same thing as mx multiplied by y, all of this prime equals mx times q of x. So we need to find a really good mx that this would be the case. And then if you write it this way, then all you need to do is just integrate the right-hand side and then take and divide it by m of x to get a solution for y. Okay? So going from here to here is just by integration. Okay? Going from here to here is just by integration. And then in order to get y of x, I need to divide by m of x, and I need to divide by m of x over here too. Right? And then I got myself my solution. So this is exactly what we're going to do now. And the question is really, what is a good integrating factor? Well, I mean, I'm just going to give you the solution, but it's usually when you have a type of, something that looks like this, the integrating factor is usually some e to the power of something that ends up being, okay? So if I use this integrating factor, e to the power of t over t2 plus I gamma r dot the integral of 0 to t g of t d tau, if I use this, then you could see that I will be able to solve this this equation. Now there's other ways to solve this exactly the same thing, using some the eigenvalues and all sorts of stuff, but the integrating factor is a simple way of doing this. Let's see how it works. This is the linear dynamic equation. Okay, this is the linear dynamic equation. I haven't done anything to it. It's just, this is what it is. Now I'm going to multiply by the integrating factor. I multiply here and I multiply here. Okay, this is the integrating factor, and this is the integrating factor. All I did is I multiplied the integrating factor by here, and I multiplied the integrating factor by here, and that equals 0. Do I have your permission to keep going? Yes? Well, let me argue that if I take mxy, I multiply by the integrating factor, and I take a derivative of the whole thing, this will result in this. Do you agree? Well, let's see. What is the derivative of a product? Is the derivative of the first element multiplied by that, plus this multiplied by the derivative of the second, right? Okay, so this is the derivative of the first element multiplied by the integrating factor. Okay, so this, right? Plus mxy multiplied by the derivative of this. What is the derivative of this? Well, it's whatever in the exponent multiplied by itself. What's in the exponent? Well, this is in the exponent multiplied by itself. Okay? Again, what is the derivative of a product? Is you take the first one, you take the derivative of this multiplied by that argument. And this is exactly this. Plus, again, plus mxy, this argument, multiplied by the derivative of this. What is the derivative of this? Well, first of all, it's an exponent, so it's itself. And then you multiply by the derivative of what's in the exponent, which is this factor. Okay? Are we convinced that this is true? Okay. So now that's nice. All I have to do is just integrate this, right? That's it. All I have to do is integrate. And the result of the integration is pretty much mxy r t e to the t over t2 plus, all that stuff. And then some constant. And what is the constant? The constant will be mxy r at times 0, right? Effectively. It will be our initial condition. Okay, so I have my initial condition. I have this multiplication here. What is then the solution for mxy of r as a function of time? I just need to take this part and divide it here, right? On both sides, right? So if I move this to the other side, this will have a negative sign. Okay? And this is exactly what I'm doing. I'm multiplying, I'm taking this, and I'm moving it over here, and the exponent of that will have a negative sign. Right, I'm dividing by this factor. Okay. I hope you were able to follow, but here's really the solution. It's mxy rt, and now initial condition multiplied by that argument that was on the other side positive, now it's negative because we divided by it. Okay, it's e minus t over t2, e minus I r dot integral from 0 to t gamma g of tau d tau. Okay? So this is a solution for the magnetization mxy as a function of space and as a function of time given an initial condition. Now, what do we see? Well, we see a few things. First of all, we see that this thing decays. This thing decays with exponential decay, e minus t over t2. Kind of makes sense, right? The transverse magnetization decays. But what's going on here? This is a complex exponential, right? That means that this magnetization vector, apart from decaying, is going to accrue phase, right? It's going to get some phase. I mean, this is a pure phase component, right? Complex exponential has a magnitude 1 and it has some phase. So this is just going to accrue phase. So what's really going to happen is, now what is phase in 2 dimension? Right? If I have a magnetization, mxy, let's say in the reals mean that I have some mx and I have my equals 0, right? That's what it means when it's on the reals. Yes? But what does it mean to accrue phase? To accrue phase, it means that this is just going to precess. It's going to precess somehow. It's going to accrue phase. Phase is pretty much a rotation of mxy in the transverse plane. Right? So the solution is really a rotation, right? It's going to be some rotation of mxy in the transverse plane. So let's stare at this long enough, you know? Let's stare at this and see what's happening. This is really spatial encoding. Why? Because you'll see that the phase that this magnetization is going to accrue is going to depend on the position, right? Because now this is the only part that depends on position, r dot something. So now the phase is going to be position dependent. Let's take a look at this and what this really is. Well, this looks like a Fourier transform, kind of, right? Like it has r, it has t, but it has all this integral at the, you know, the exponent, you know, it's kind of like annoying, right? Like it has this integral over here, that's kind of annoying. So what I'm going to do is I'm going to call this thing with a different name. So the integral from 0 to some t, gamma g of tau d tau, I'm going to call it something else. Okay? I'm going to define a special frequency vector k of t, which is going to be gamma over 2 pi integral from 0 to t g of t d tau. That's going to be k of t. Okay? And I'm going to try to substitute this into here. Now this is a solution for, you know, just a linear dynamic system, right? That's the solution we got. Now we're going to use linear algebra and just substitute this integral with k of t. Let's see what happens there. Well, what happens is that mxy r of t equals mxy r 0, e minus t over t2. Yeah, we've seen this before. And then instead of having that integral over here, I replaced it with k of t. And so here I've got e minus I 2 pi k t dot r. Okay? Now, folks, this now looks like a Fourier kernel, right? This looks like a Fourier kernel. What is a Fourier transform? If you remember, S of t equals, sorry, not S of t, S of k in 1D, capital S of k, equals the integral from minus infinity to infinity of, what is the Fourier? S of t times e to the minus I 2 pi k times t dt. You agree? If I want to not do t, I want to do x, for example, I can replace the t with an x here. Now it's a spatial position. It doesn't really matter. This is the Fourier. This is a Fourier integral. So this looks like a Fourier kernel. It has I 2 pi, has a k, and it has a spatial position, right? So k and x in this case. Here it's just three-dimensional, right? So kx, ky, kz, x, y, and z. Does that make sense? So this is the Fourier kernel, but this is not a Fourier transform. This is not a Fourier transform. It's close, but it's not a Fourier transform just yet. This is our magnetization at particular position at particular time. What is though the signal that we receive? We put a coil next to a sample. The coil receives the signal from the entire sample. So the integral over space of all those mxy's. Remember, the signal that we receive is proportional to mxy. But it's all those mxy in the volume together. So our signal is the integral over the entire space of mxy of this, right? Of mxy. What is this? Well, it's mxy at, space position at time 0, e minus t over t2, and then a Fourier kernel. Okay, but it's the integral over the entire R, over the entire space. Now this t2 is also a function of R that can make it also complicated. We cannot really take it out if we wanted to, right? And it's a function of, time too. So, folks, this is not a Fourier transform. This is not a Fourier transform. It's close, but it's not a Fourier transform. What we're going to assume now is we're going to assume that T2 is very large. If T2 is very large, then this value over here doesn't change much over a large range of T's. What if T2 goes to almost to infinity? What's this value? How does this function look like as a function of time? If T2 is very large, let's say it's infinity.
It's just 1.
It's just 1, right? It's a constant. Yes. So if T2 is large, or the time scale that we're looking at is very small with respect to T2, then we can say, oh, this is constant throughout the time that we're looking. Is that a good assumption? Is that a good assumption? Is this a good assumption? What's the answer? It depends.
Depends.
Right, it depends. It depends how long we're going to read and how fast our signal decays. If our signal, if it's just pure water and T2 is like 3 seconds and we're going to read for maybe 1 millisecond, yeah, that's a really good approximation. But if our T2 is, 20 millisecond and we're going to read for 20 millisecond, well, that's not a valid approximation anymore. And because it's not a valid approximation, and if we still use this Fourier analysis, we're going to get artifacts. And you're going to see the artifacts that we're going to get later a little bit when we do image analysis. You're going to see it's going to result in blurring, but we're going to get to that, okay? But right now, we're just going to assume that it works out and we can ignore it. And if we can ignore it, if T2 is large, then this is really the equation that we get. Now look at this. Oh, now it has a Fourier form. Finally, it has a Fourier form. Look, it's the integral over the entire volume of the magnetization in its initial state times e to the minus I 2 pi k of t dot r dr. This has a Fourier form. This is effectively, our signal is then the evaluation. It's the Fourier transform of the magnetization at time 0. Whatever our magnetization was at time 0, I'm going to compute now a Fourier transform of it, and I'm going to evaluate that Fourier transform at some k. What is this k? What is this k? Well, k is a function of g, right? K is a function of g. It's an integral of g, right? So the gradients that I apply are going to affect k, and in turn, I'm going to evaluate the Fourier transform at certain k's that depend on what gradients I'm applying. Okay. So this is the solution. Really, my signal is samples of the Fourier transform of mxy, of the distribution of mxy as a function of space. It's a spatial distribution at time 0. It's initial condition. It's immediately after excitation. Whatever mxy was after excitation, I take a 2D Fourier transform of this, and then my signal is evaluation of this 2D Fourier transform at those k's. What those k's are? Well, that depends on what g's I'm applying. Depending on what g is, I can find what k is, and if I know what m of x is, then I can also compute what s is. Does that make sense? Okay. So it's really an example for a transform along a certain trajectory. And let's see what it really means. Okay. Kt, this k, this mysterious k, is what's called a k-space trajectory. It's the integral of gamma over 2 pi, integral from 0 to time t, to some time that I'm interested in, of the gradient waveform. So it's in fact, it's the area, it's really this part is the area of the gradient that I apply. If I apply a constant gradient, you know, right? If I apply a constant gradient, then the area increases linearly. And hence my k will increase linearly over time. But if g of t doesn't have to be constant, it could vary. In that case, my k is just the integral of whatever that area is. Okay, so this is the area of a gradient waveform. So effectively, what I have here is Etch-a-Sketch. Okay, and bear with me. Okay, bear with me. We don't control k directly, right? We control g. G controls k. K is the integral of g, right? So this is very similar to an Etch-a-Sketch. You know what's an Etch-a-Sketch? It's this, it's this board where you have, two buttons that you rotate. And if you rotate the X, you have like a dot. If you rotate the X, the dot will move in the X direction. If you rotate the Y, then it will move in the Y direction. Then I can move G in the, the X in the other direction, and so on and so forth. So effectively, my position is the integral of what am I applying, the rotation. That's why it's similar to Etch-a-Sketch. Okay. So effectively, we control G. Where we are in K is the integral of G. Is the integral of G. Is the area of our contribution, where we are. Now, how can I control G? Well, normally it has no limits, except, of course, there are some hardware limits. The hardware limits is that my amplitude, how strong G is limited. Okay, and it's about 4 Gauss per centimeter. What does that mean? That the integral, if G is maximized a certain amount, that effectively means that how fast I travel in the frequency domain is going to be limited. The velocity is going to be limited. Okay, because if I have very, very strong G, then the integral of G will be varying very fast. And so I will move very fast. If G is small, then the integral is, grows slower, then I will move slower. But effectively, I have a maximum G that I can apply. Hence, I have a maximum speed that I can go. Okay. The other thing is that, so effectively, the first derivative of the trajectory of the K-space trajectory is going to be limited. The other limitation is that also how fast G changes, the gradient changes, is also limited. And that limits the second derivative of K. So the first derivative of G is limited, that limits the second derivative of K. Also, the maximum of G is limited, and that limits the first derivative of K. Effectively, that limits how fast I travel in the frequency domain. It also limits how fast I can turn, or I can accelerate, or can speed up. Remember, where I am in K space is the integral of G, and hence my speed in K space is limited, and also my acceleration in K space is limited. So I can't just go like this very fast, but I'll be limited by, how much I can accelerate. Maybe if I want to do a spiral, I won't be able to actually go very fast along the spiral because I'm going to be limited by how fast I can change things. If I want to go back and forth like this, then I will be limited by how fast I can go. And when I turn, how fast it takes me to slow down and accelerate again, and then reach a maximum speed, slow down, turn, accelerate again, and so on and so forth. Okay, these are going to be my dynamics. Okay, so what are the limits? Well, the limits are the gradient maximum is about 4 Gauss per second. The slew rate is about 15 Gauss per centimeter per millisecond, or 150 Tesla per meter per second. These are the values. And the effectiveness is that it takes about 267 microseconds to start from a gradient which is 0 to a gradient that is maximum 4 Gauss per second 4 Gauss per centimeter. So if I want to turn on my gradients from the lowest value, or sorry, from 0 all the way to the maximum value, it will take me 267 microseconds to do that. Does that make sense? So it takes time to ramp up. Okay? So because the derivative of K is limited and the second derivative of K is limited, K is effectively a always smooth and always continuous. So our K-space trajectory is always smooth and it's always continuous. Okay, that's the effect because it's the integral of G. So it's always smooth and continuous. So the question is really what type of K-space trajectory I'm going to do. And you can think of it as an etch-a-sketch. An etch-a-sketch where I start, let's say at this point, and then I rotate X, and then X moves me in this direction. And then I rotate Y, and then Y moves me in this direction. And then I rotate X the other way, and then that moves me in this direction. And all the same time, I collect measurements in that frequency. Think of this space. Think of this space as the two-dimensional Fourier transform of the object. And by changing G, X, and GY, I can travel in this frequency domain and collect measurements. That's the idea. Okay. Is this concept is very, very important. Okay. We showed that MRIs effectively calculates the two-dimensional Fourier transform for you. And then using the gradients, you travel in this Fourier transform and collect measurements. And so your time signal, the time measurements that you make, depend on what G is and what is the Fourier transform of the image. Okay. So in some way, the time measurements are collecting data in the spatial Fourier transform of the object. Does that make sense? Because the signal is S of t. S of t is a function of k, right? What is k? K is a function of g, right? So, so this is something that you have to kind of absorb, and I'm going to give you some example, and hopefully you'll be able to understand kind of what I'm talking about. But when I talk about that stuff, I want to talk about the case of slice selective 2D example. In slice selective 2D, we select a slice in Z. So our Z, only a thin slice of the spins in Z are being excited. So the rest of the volume is not going to contribute any signal whatsoever. So all we have to do is encode the image in X and Y directions. That's the only thing that we have to do, because the image is being integrated over Z. But it's a very, very thin slice. So if you think about it, S of t is the integral over X over Y over Z of the magnetization, which is three-dimensional. The magnetization is three-dimensional. And then e to the minus I 2 pi k of t dot r. Okay. Now, if you remember, because we're not going to apply any gradients in Z, but we only acquired a very thin slice. Only a very thin slice in Z is being excited. So effectively, our signal is being integrated over the Z direction. Now, what does it mean? What does it mean to not apply a Z gradient, a GZ gradient? That means that the integral from 0 to t of G Z of tau, d tau, is always going to be 0. That is kz. The spatial position in k-space in the Z direction, when we do slice select, is always going to be 0. It's all going to be dc, right? It's just the integral over that dimension. So effectively, we're just integrating over Z whatever we have. So we're just assuming that the slice is pretty uniform in Z. It doesn't change in Z. Hence, we just get, whatever, basically we integrate along that dimension. And then the rest is Fourier encoded. Okay. Does that make sense? It's a little bit hard to absorb, but let's look at some examples. Here's an example. So the question, first of all, that we have to ask ourselves, when we collect data in the frequency domain, we need to ask how far in the frequency domain we're going to collect data. That is the extent. And how far is going to correspond to what is the image resolution. The furthest we go in the frequency domain, the higher the spatial frequency we're going to collect, and then the image is going to have higher resolution. And then the density that we're going to collect measurement, that's going to be proportional to the field of view we're going to talk about next time. Now, often the k-space coverage would be square, but sometimes it could also be circular. So it depends. And so the question is, like, what are the options to collect data in this domain? So here's a very simple example. In this example, we apply a slice selective RF that selects a slice through our volume. Okay? Our image, in this case, we're going to consider it as a box. Okay? This is the X dimension, this is the Y dimension, and the image M of X and Y is going to be 1 over here, and M of X and Y is going to be 0 outside of the object. Okay, so our image is a box, is a two-dimensional box. Okay, all right. So by doing this, we effectively, if we had a three-dimensional volume, now we only have a two-dimensional image to encode, right? Because we only excited a slice. Now I'm going to apply in the X direction some negative gradient in the X direction. Then I'm going to apply some positive. And then here I can apply an optional negative. And then during this time, I'm going to collect data. The question really is, what is the K-space trajectory that I'm collecting? And what is my signal, S of t, in terms of my analog to digital output? Like, what am I actually receiving? Okay, so let's try to actually do this analysis. Okay, and the way I'm going to do this analysis, I'm going to break this trajectory, this period, into three parts. Part 1, part 2, and part 3. And we're going to try to figure out what's going on within each part. Remember, here we applied an RF, we apply a gradient to do the selection. There's this weird stuff that I haven't talked about yet, but I'll talk about later. And then from here on, the RF is off, right? There's no RF. So we're in the reception stage. And now I want to perform an analysis and see what my signal that comes out. Okay. So what is my signal? Well, the first thing I'm going to do is take the two-dimensional Fourier transform of this image. The two-dimensional Fourier transform of this image is a 2D is a 2D. What's the 2D? What's the two-dimensional Fourier transform of a rect?
Sink.
Yes, it's a sink in X and a sink in Y.
Yes.
Multiplied by a sink in Y. Okay. So now, immediately after excitation, what is the integral of my gradient? What is the integral of gx immediately after the excitation? This is times 0. This is times 0. So what is the area underneath x? Gx?
It's the 0.
Is 0. So what is kx?
0.
Right. What is ky?
0.
That's right. So immediately after, at this point over here, if I would have collected the signal, then the signal would correspond to the value in k-space here. So it would be basically the value at DC, kx equals 0, ky equals 0, of that two-dimensional sink. So it's going to be this value. It's going to be a large value, I guess, right? It's going to be bright. Okay. And then what happens after that? After that, I'm applying a negative gx. So how does my k vary with time? How does kx vary in time?
It'll become more negative.
Right, it's linear, right? It's linear, and it becomes negative, right? It's linear and becomes negative. So it's a linear function. Kx is a linear function, right? And it starts at 0 and it becomes negative, right? At what rate this is changing? Well, at the rate of the, basically is the integral, right, of gx. So if gx is large, then that slope is going to be large. If gx is small, that slope is going to be small. So the velocity that I go from here and I start moving, and I collect samples. I collect samples during this time. What would my signal look like? My signal would look like a sink during that time. Sorry, let me change the color. It's supposed to be red. So during my time, my signal is going to start high, and then it's going to look like a sink. Half a sink, right? It's really just this part of the frequency domain. Then at this point over here, I change the polarity of the gradient. And now the gradient, I apply a positive gradient. What is k? Well, k is the integral from the beginning all the way to my time point. So effectively, k starts increasing linearly from being negative all the way to being positive. That's the same as going from here in the frequency domain and collecting samples, which are the cross-section of this two-dimensional function. I'm collecting samples along this trajectory of this two-dimensional function. And what are the values of this function going to look like?
Sink.
A sink, absolutely. And it's a green sink now, because and when it's the maximum is going to be in the middle, right? Because when I cross the middle, that's where it's going to be the maximum, and then it's going to decay like that. Does that make sense? And then I have an optional negative third, which will then take me possibly back to the center. If I go back to the center, then the integral over the entire thing at the end will be 0, right? Like if I integrate over the entire thing at the end, you know, the area of this and the area of this is negative, and it's the same as the area of this. So the result will be 0. So I'm going to come back to k equals 0, right? And so there I will collect, it's in blue, I will collect value like that. Interesting, huh? So this would be my time signal. This is my time signal. And it was like this because I apply a negative gradient in x, and then a positive, and then a negative after that. Whereas this has twice the area of this one. So effectively, I went half as far, went all the way to the other side, collected data, and then potentially came back. Now, why to come back? That's a good question, but you don't necessarily have to. Okay. So effectively, I went to the left. Now I collected data, and then I went back to the center. And if you think about this, then I'm collecting what is the value of this two-dimensional function along this trajectory. And that value is going to look like this. If I would measure the signal from the coil, it would look exactly like a decaying sink, a full sink, and then, you know, the other half. Because I went half a sink, full sink, and then back half a sink. Does that make sense?
Question.
Okay. Yes.
So the sink is still going to be modulated with the RF signal, right?
Yeah, this is the base. So this is the baseband signal. Of course, all of this is being modulated by j omega 0, either the minus j, which is the Lamor frequency. It could be, 64 megahertz at 1.5 Tesla. It could be 127 megahertz at 3 Tesla. Absolutely.
Yes. So we are looking at the envelope.
We don't. Yeah, we're looking at the envelope. Absolutely.
Okay. Thank you.
Yes. Okay. So now the question is, how do I collect the entire Fourier transform? So what I could do is I could keep the exact same thing. This was my GX before, right? Now I'm going to apply a GY that's exactly the same as GX. If I do that, then I would, my position in GX is going to be negative, right? Up to this point. Up to this point, my K is going to be more and more negative in X. It's going to be more and more negative in Y. Hence, I will travel along the blue trajectory in 45 degrees. And then if G of X is positive and GY is positive, and they have exactly the same value, I'm now going to travel along 45 degrees and cross to the other side. So now I can do, you know what? I can multiply this by cosine of some theta and this by minus sine theta. And then every time I'm going to change my theta. And that would lead to pretty much reading this line with some other theta, and then reading this line with some other theta, and then reading this line with some other theta, and then reading this line with some other theta, and then reading this one with some other theta, and then I can cover a whole circle. And then I will effectively be able to get the two-dimensional Fourier transform in polar coordinates. Okay? How do I reconstruct from Fourier transform in polar coordinates? That's a good question. I can use the same mathematic as CT, or I can perhaps interpolate onto a Cartesian grid and then do a 2D Fourier transform then. I mean, there's many ways. If anybody's interested of doing a project on non-uniform for FFT or the gridding algorithm, this is an algorithm to reconstruct data from non-uniform samples in the frequency domain. You can do a project on that. That could be a very interesting project. So quickly, what I want to say is that we don't have to do that. We can apply a sequence that looks like this. Again, this is slice selection. And then after that, I have the typical GX that I had before, but then my GY has a blip like that. In that case, what would be my K space as a function of time? Well, I can also, break my sequence into period 1 and period 2. So what would happen in period 1? Well, period 1, I integrate over X, I integrate over Y. Integrating over X, I will get negative, more negative, and more negative K in X direction, and more positive and positive Y, KY, right? Because it's the integral over Y. And so effectively, Kx will become negative, Ky will become positive, and effectively I will travel in the frequency domain in a diagonal. Now I'm going to stop Gy and I'm only going to apply Gx. Okay, so Ky, what's going to happen to Ky as I continue on? What's going to happen to Ky?
The same value.
It's stay the same value because the integral from this time point all the way, right? So it's the integral, so it's going to stay the same value. What about Kx?
It'll move to the right.
It's going to increase from the negative side all the way to the positive side, right? So it's going to, so Ky is going to stay the same, and Kx is going to go from negative to positive. Okay, so in that case, I'm effectively collecting this line in the frequency domain. So S of t would correspond to the evaluation of this 2D Fourier transform at this line. My time signal is going to be the evaluation, the Fourier transform along this line. And now I can repeat my experiment. I can change my GY to be, for example, smaller. If I change it to be smaller, then I will travel up to here and acquire this line. And then if it's negative, I will actually travel here and acquire this line. And actually, this way, I could collect samples along Cartesian trajectory, much more simple than along a polar coordinates. Right now, I have things on a Cartesian coordinates. Next time, I'm going to elaborate on this. This is called spin warp, and or 2DFT, and it's a way to apply a sequence of gradients such that we collect the data on a Cartesian grid. And then all we need to do after that in order to reconstruct an image is a two-dimensional Fourier transform, which is pretty amazing. Okay, so I stole some time. I apologize for that. On Thursday, we're going to elaborate more on that, and we're going to give some more examples of these trajectories and how to go about and evaluate of what is actually being collected, okay? And what is the process of you to go and do the analysis to figure out what is the data being collected, okay? So we'll do that on Thursday. So hopefully now you have a better idea of what's going on. But on Thursday, we're going to solidify this knowledge. Okay. All right. Have a nice day. Tomorrow there's still a discussion. We're going to solve some problem, maybe related to that. Okay. All right. Take care, folks. Thank you for sticking up with me.